The integrated rate laws gave us a theoretical basis for the relationship between concentration and time for different orders of reaction, m equals 0, 1, or 2. So one way we can determine reaction orders is to measure concentration versus time for a reaction, and then simply fit to zero order, first order, and second order models and see which fit works best. That's one way to measure reaction orders. Another way is to use what are called initial rates. Initial rate methods have the advantage that we don't have to run the entire reaction. We're only concerned about the rate of reaction at the outset, at the very beginning. But the disadvantage is we have to run a lot of reactions to isolate the effects of particular reactants. It's a pretty versatile method though, and one that works much better for reactions with, for example, more than one or more than two reactants, where it's difficult to isolate the orders of particular reactants. Let's first define what we mean by initial rate. The initial rate of a reaction is the rate at the moment the reactants are mixed. So at the moment the reactants are mixed, we have some initial concentration. Let's look at a hypothetical reaction AA plus BB goes to a single product, CC. We have some initial concentration of A at time t equals 0, and the initial rate of the reaction, if we're following the concentration of A, is the slope of the concentration versus time curve at the initial time point. More formally, it's the instantaneous standard rate at that initial time point, t is equal to t0. In an experimental context, we're going to have to be measuring a particular concentration, like the concentration of A, and so it would be negative 1 over A dA dt evaluated at t is equal to t0 at the initial time point. Initial concentrations dictate the initial rate of the reaction because the rate law still holds even at that very initial time point. Hence, we can be clever about the way we choose initial concentrations to reveal kinetic orders, and we'll see how this works through an example. But the basic idea is to, for example, start with A0 equal to 1 mole per liter, and then do a second run of the reaction with the initial A concentration equal to 2 moles per liter, and see what the resulting effect is on the initial rate. With all other things being equal, we can isolate the influence of the concentration of A on the reaction rate. That's the beauty of the method of initial rates. There is a catch here though. The catch is that many runs are required, and rapid measurement of concentrations is essential so that we can get accurate values for the initial rate. Just to show you what happens if we don't have rapid measurement of concentrations, imagine in actuality the concentration of A is changing something like this. The instantaneous rate is actually quite rapid. It would be something like this red line here. But say we're only able to measure the reaction at t0 and say at a second time point out here. Now the initial rate looks much slower than it is in actuality, since the line connecting the 2 points in black is not as steep as the red line, the true instantaneous rate. That's why rapid measurement of concentrations is essential, which these days is not terribly hard to prepare, but it is an important issue to consider. Another important issue is that multiple runs are necessary. We need a run, for example, where A is 1 mole per liter initially, and another run where A is maybe 0.5 moles per liter initially. That's 2 setups of the reaction, and that's 2 reaction runs. So if material is precious, that can present problems. So let's look at an example of the method of initial rates. Given the data below, what are the orders M and N for NO and H2? The reaction here is 2 molecules of NO combining with 2 molecules of H2 to make nitrogen gas, and 2 molecules of gaseous H2O. We want to know what are the exponents on the reactants, NO and H2, in the rate law, and we can discover this using the method of initial rates. In a method of initial rates problem, you're going to be given different trials, and the concentrations that are used initially, these 0 concentrations, the concentrations at time t equals 0, are going to have some special relationships to each other, and you want to look out for these special relationships. So for example, if we look at the concentration of NO initially in runs 1 and 2, what we find is that the concentration in trial 1 is 5 times 10 to the negative 3, and the concentration in trial 2 is 1 times 10 to the negative 2. If you divide these two by each other, you'll find that, for example, this concentration is 1, and the concentration in trial 2 is twice that. It's equal to 2. Check out the initial concentrations of hydrogen gas. In run 1, we've got 2 times 10 to the negative 3rd power. In run 3, we've got 4 times 10 to the negative 3rd power. If we set this concentration equal to 1, The concentration in trial 3 is double the concentration in trial 1. That's a strategic choice. Notice also that in run 2, we've left the concentration of H2 the same. This is a control measure, such that between runs 1 and 2, the only concentration we're changing is that of NO. Between runs 2 and 3, we leave the concentration of NO constant. This is also a control measure, so that the only thing we're changing between runs 2 and 3 is the concentration of H2 gas initially. Since the rate law must hold for all 3 reactions, we can write the rate law for all 3 reactions using these concentrations. So for example, in trial 1, we can write that the rate 1 is equal to some rate constant, which is going to be the same for all of these since the rate constant does not depend on concentration. The initial concentration of NO, which I'll write as 5 times 10 to the negative third, to the M power, times the initial concentration of H2, which is in this case 2 times 10 to the negative third power, raised to the N. And we can do the exact same thing for trial 2. The second rate, R2, is equal to K times the concentration of NO initially, which is 1 times 10 to the negative second power raised to the M, times the initial concentration of H2, which is still 2 times 10 to the negative third power raised to the N. Now what I want to do is divide equation 2 by equation 1. You'll see why I want to do this in a second. What it's going to do is allow me to isolate M, make M the only remaining variable such that I can solve for M. On the left-hand side, I get simply R2 divided by R1, the initial rate for the second trial divided by the initial rate for the first trial. And do notice, coming back to the table, that I have these numbers in a table, and I haven't quite plugged them in yet, but we will here in a second. The k's actually divide out when I do this division problem, as do the factors of 2 times 10 to the negative third to the n. The initial concentrations of H2 divide out. What I arrive at then is that this ratio of the two rates must be equal to 1 times 10 to the negative second power divided by 5 times 10 to the negative third power, all raised to the power of m. Since both were raised to the power of m, I could collect them both inside this exponent expression. These concentrations were strategically chosen so that this is equal to 2. And so we can write this as simply 2 to the m power. So now we return to this ratio of the rates, and we look in the last column of the table for runs 1 and 2, or trials 1 and 2. What is the ratio of R2, 5.2 times 10 to the negative 5, to R1, 1.3 times 10 to the negative 5? Well, that's 52 over 13. That's equal to 4. So now we're solving a very simple equation. 2 to the m is equal to 4. And you could solve this in general by taking the logarithm of both sides and doing some division, but ultimately, by inspection, we can see here that m must be equal to 2. That means that this reaction is second order in NO. We've figured out the value of m. We can do the same dance with H2. To save us a little bit of time, I'll jump ahead a bit and say that when we divide the rate laws for trials 3 and 2, we get 4.0 times 10 to the negative 3 divided by 2.0 times 10 to the negative 3, all raised to the n power now. The factors due to NO drop out. That's equal to the rate of the third trial divided by the rate of the second trial, which in this case is 1.04 times 10 to the negative 4 divided by 5.2 times 10 to the negative 5. Well, that's 104 divided by 52, which is equal to 2. This whole thing here is equal to 2, so 2 is equal to 2 to the n power, which means n must be equal to 1. And we've concluded that the reaction is first order in hydrogen gas. So the method of initial rates is pretty powerful and pretty intuitive. What we're doing is using strategic concentrations of the reactants, usually just doubling them, leaving everything else the same and looking at the effect on the initial rates. By dividing the rate laws by each other and then isolating the exponent as the only remaining variable, we can solve for the value of that exponent.